Guys, hello, welcome back. Um, Before we get started today, finally starting to see some applications of these quadratic functions, let's just do kind of a practice again, reteach like we would do in class. So what I'm going to ask you to do right now is in your homework last night, you should have hopefully a coordinate plane that you could do 2 more graphs on. So I'm going to ask you to just graph 2 more. So the first one here is y equals 2x squared minus 5x plus 1. So what I'd like you to do right now is pause the video, graph this, come back, and we'll see how you did, and then we'll do an inequality. Okay, now that we're back, to graph a quadratic, the first thing we're going to do when there's a bx term is we are going to take the opposite of b, which in this case would be the opposite of -5, over 2a. So did you start by getting 5/4? There's nothing saying that you have to keep that as a fraction. So how about if we make it a decimal? That is the x-coordinate of our parabola. To get the y-coordinate, I'm going to take out my calculator and I'm going to take 2 times 1.25 squared minus 5 times 1.25 plus 1, and I get the y-coordinate of -2.125. So if you didn't get the vertex right, the whole parabola could go off. So please make sure you understand that. Now this one is kind of a nasty one to graph. So if I go to graph this one, and I go to 1.25, -2 and a bit, I mean, the vertex is somewhere around there. And here is one of those cases that trying to use that axis of symmetry right now is going to be a little bit confusing. So what I would do instead is I'm going to do the math 5 times. I already did it once. I'm going to pick 2 values to the x values to the right and 2 x values to the left. And it doesn't matter that they're symmetric. So I'm going to pick 0 and 1, which would be 2 x values to the left, 2 and 3, which would be 2 x values to the right. And I'm going to just substitute those in. I'm going to put in x equals 0, do the math, get 1, put in 1, so 2 times 1 squared minus 5 times 1 plus 1, get a point. I'm going to put in 2, and you're going to notice as I do these 4 values that their symmetry is missing that we saw the other day. That's okay. And I'm going to plot those 5 points, and it will form a U, and I will draw that in, parabola I should say, and that's an okay way to do it. So the axis of symmetry does exist, and you could use it here if you don't mind doing kind of working off the quarter here. But you can always just pick 5 inputs, but just make sure you're building around the vertex. And that's why I picked 2 from the left and 2 from the right. Let me just show you what that looks like. So you'll notice my 5 points are there and they're forming the parabola, but they're not across the axis of symmetry from each other. And who cares? You can absolutely do it that way. I just want to mention now while I'm thinking of it, don't forget to put your arrows on, because when we think about the range of this function, it's not going to stop here. It's going to continue up to that positive infinity. Okay, let's take a look at another one. How about y is less than or equal to x squared plus 5x plus 6? Why don't you pause the video on this one and see how you do? Okay, now that you're back, what I'm going to do this time is I'm just going to put up the answer here and talk it through if you don't mind. So let's start with our vertex. You would have taken -5 divided by 2 times 1. -5 divided by 2 is -2.5. Don't forget when you substitute in that you needed to catch this in the glove, so you needed to square -2.5, and in the calculator you need to put that in parentheses before you hit the squared. Your y value should have been -2.5, so you'll see -2.5 and a little bit down, and that's where my vertex is. Now this time I'm okay working off the halves with the axis of symmetry, so you know using the -1 and the -4, and also I used the 0 and the -5, and and I can build around that. So I substituted the -1 and got an output of 2, and I plotted that point, and then I went 1.5 to the axis of symmetry. So if I go half and then 1, I can use the axis of symmetry comfortably. But remember from the last example that you are welcome to do the math by substituting in. Don't forget that the C always gives us the y-intercept. So, 0, 6. And then again, I went in the other direction from the axis of symmetry and was able to get that y value as well. Now, remember, it's really easy to forget that this is an inequality. At the end, you get so busy, and we need to do some shading. It would be a solid parabola. That's why this guy is not dotted. The points on the parabola are included as part of the solution this time. And then I decided to pick 0, 0. He's far enough away from the parabola that I'm confident, that that's a good point to test a region. And you'll see down here that I rewrote the inequality, replaced the x's with zeros, and you get 0 squared plus 0 plus 6. Is 0 less than or equal to 6? That is a true inequality. So 0, 0 is part of the solution. So I shaded all here. So every single point in this pink shaded area would make this inequality true. But these guys in here, for instance, -3, 5, if you substitute -3 in for x and 5 for y, it will not make a true inequality. Okay, so that was kind of a quick reteach of graphing when we have that bx term, but we really need to get on to answering, where do we use this stuff? So this is a really, really good picture, and we're going to do some what's called vertical motion models. So I want you to imagine that I'm standing in front of the classroom, and I throw a tennis ball straight up towards the ceiling, and I catch it in my hand, vertically straight up. I don't throw it forward or to the right or to the left. I'm perfectly straight up and down, vertical motion. If I had one of you sitting at the back of the classroom and you were taking pictures of the ball going up and down, sort of like very quickly, like they do in sports photography sometimes, I want you to imagine that we take a series of pictures, maybe every quarter of a second, and then we take those pictures and we line them up next to each other. So, here was the height of the tennis ball when it left my hand after a quarter of a second, after a half a second, 3/4 of a second, a second and a quarter. And you can kind of see if you put the pictures next to each other. So here's the quarter of a second went by, it's this high. A half a second went by, it's this high. 3/4 of a second went by, it's this high. And then a second went by and it's this high. And you can see that as we go to the right here, we put the pictures next to each other. The ball is getting higher. It maxes at the vertex, and then it's going to come back down. Now, this is not a picture of the actual motion of the ball. It's what happens as time goes by. The ball is just going to go up and down if you're watching it. But if we took pictures and put them next to each other, we would see that parabolic curve, which is a quadratic. So notice that the x-coordinates of all of these points that are represented by tennis balls represent time, and the y-coordinates of all of these points represented by the balls would be height. So when we look at the vertex right here, this is the highest point, the highest tennis ball, the x value of that vertex, so the x value I'm drawing right up there, would be how much time it took for the ball to get to the max, and the y-coordinate of the vertex, which would be over here, the y-coordinate would be the height, how high the ball went. So the x-coordinate of the vertex is how much time it took for the ball to get to its highest point, and the y-coordinate would be that height. What is the highest point? That's going to be important as we go on to do a couple of problems. So let's start with a firework. An aerial firework at a starting height of 520 feet. So imagine that they're setting up the fireworks on a hill that's 520 feet above sea level. They're going to shoot out of those cannons with an upward velocity of 72 feet per second. Now I'm going to give you the equation right here. Not too long in the future, we will be able to write this ourselves, but I want you just to notice some things. This is going to be the equation of the t is going to represent how much time in seconds goes by, and the h is going to represent how high the firework is in feet. So the t variable is time in seconds, and the h variable is height in feet. But I just want you to notice something before we go on. Do you see that 72 feet per second? Just notice that he happens to be the B. Did you notice that the 520 happens to be the C? And interesting enough, I don't know where this negative 16 came from, but I just want your eye on that. So here I've given you the equation, and we have to answer two questions. How long, how much time will it take for the star to reach its maximum height? So how much time before it maxes out? And then part B, how far above the ground will it be? What will that height be? There are two questions. Both of these questions come from our vertex. It is asking about the maximum point. Since this is a parabola opening up downwards, the vertex is its maximum point. The x coordinate, in this case the t coordinate represents the time it takes to get to that maximum height. And the h of the vertex, the y coordinate, is the height, how high up in the air it is. So when it asks how long will it take for the star to get to its maximum height, it is asking for the x coordinate of the vertex. That's easy. Negative b over 2a. I'm going to take negative b over 2a. Negative 72 over 2 times negative 16 is negative 72 over negative 32, but the two negatives cancel out. I'm going to pick up my calculator and divide 72 by 32, and it's going to take 2 1/4 seconds, 2.25 seconds. That firework is at its highest point and will explode. How far off the ground will it be? So at 2 1/4 seconds, it will be at its maximum height. But what will that height be? That 2.25 is going to replace these t's, and I'm going to do the math in the calculator, guys. So this goes into the calculator. You know, I always kind of catch things in the parentheses. In this case, the parentheses aren't necessary in the calculator because it's positive. So negative 16 times 2.25 squared plus 72 times 2.25 plus 520, and I will get the height. I add those all together, and it will be 601 feet in the air. So as I see the fireworks explode, it ignites, rather, it takes off. 1, 1,000, 2, 1,000, boom, it will explode in 2.25 seconds. And where will it be in the air? 601 feet. Okay, I would like you to try this process on the next problem. So we'll read it together, and then I'm going to ask you to do two parts. So first, a ball is thrown into the air with an initial velocity of 48 feet per second. And again, we're going to assume vertically straight up in the air. Its height, h, in feet after t seconds is given by the function h equals negative 16t squared plus 48t plus 4. In how many seconds will the ball reach its maximum height? We'll answer that question in a second. Before we go anywhere, do you see that 48 feet per second going in front of the t again? Just like in the last example, that 72 was the B. I hope you start to notice a pattern. It'll be important in the future. Notice that the A is negative 16, same as here. So that has something going on there with vertical motion. And this time, it's not really talking about what the 4 is, but I'll give you a little clue. When you throw that ball up out of your hand, when you release it, it's not on the ground. It's about 4 feet off the ground. Now, you didn't need to know any of that, but you will in the future, okay? So here is the function that will model the movement of the ball vertically being thrown up with that velocity. How many seconds will the ball reach its maximum height? First of all, it's a parabola. It is a quadratic function. Negative a means that the parabola is going to open down. I hope that's what you remembered. The maximum height is going to happen at the vertex. It's going to rise up and then it's going to fall down. So the highest point will be at the vertex. The time of that maximum height will be which coordinate, guys? Think about it. It's going to be the x coordinate. So what I need you to do right now is please find the x-coordinate of the vertex of this quadratic function. Pause the video, see what you can do. Okay, now that you're back, let's see what you did. Negative b over 2a. So negative 48 over negative 32, which is 48 over 32, and pick up your calculator. 48 divided by 32. I reduced it first, but you should have gotten 1.5 seconds. So it's going to take 1.5 seconds to reach the highest point. Well, the question is, what is that highest point? What is the number of feet that it would be in the air? That's part B. So the question is, what is the ball's maximum height? The maximum height will be the what coordinate of the vertex? Did you think why? I hope so. So can you right now find the y coordinate of the vertex? Please pause the video and see how you do. Okay, guys, we need to find the y coordinate. We had already found the x coordinate, which in this case we're using t. Remember that science will often bring different variables in. In this case, t is our independent variable, which on the coordinate plane would be x, and h is the dependent variable, which again would be y. So we're going to let t be that 1.5, which was the negative b over 2a, and we're going to substitute it in both t spots, and we're going to put this in the calculator. Once I put it in the calculator, you should have gotten that it is 40. 40 what? 40 represents height, and in this case, the units are feet. So after 1.5 seconds, with that upward velocity of 48 feet per second, the ball would be 40 feet in the air. So we have done 2 examples of vertical motion, which is one of the applications regarding quadratic functions. So we're finally starting to answer the question of, where are we going to use this stuff? So I'm asking you tonight to do a little bit more graphing of quadratic functions with the bx term, and also to start applying it to vertical motion. Guys, I hope you have a great day.